So while this takes a second to load, is anybody still having trouble with mastering A&P? Is that working okay? So just a reminder, the extra credit chapter at Mastering A&P is due Monday. So it's chapter 14, which we've already gotten into a little bit, and you have a 3-question quiz up. Okay. So before I get started talking, I wanted us to take a second practicing what we learned on Wednesday about the relationship between flow and pressure. Today we're going to be adding in understanding this idea of resistance. Take a second and look at this figure on the board. I have our initial pressures listed for locations A and B. We want to think about what happens if those pressures change. Who wants to start out by reminding me about the relationship between flow and pressure? We looked at an equation, so you could give me the equation, or we use a mathematical term to describe this relationship as well.
Pressure over resistance equals flow.
Yeah, exactly. So we had our flow, we had our difference in pressure. So that's what this triangle is. Right, so the triangle means we're looking at a difference. Is important to remember, divided by our resistance. Okay. So for this first question, actually, let's start out. So given this initial situation, which direction would we expect our, let's just say it's blood to be flowing? Going to be going to the right or to the left? Okay, so we're going to the right, right? So we're going from A to B, not a trick question. This is because pressure has gradients, right? And we're always going to be expecting our flow to move along that pressure gradient. So we're going from our high pressure of 100 to our lower pressure of 50 in our initial situation. So the next piece of information is we're saying A increasing by 50 millimeters of mercury. So now we're at 150. Now remembering what our relationship of flow and pressure is, what would we expect to be happening to the flow? Let's think of that flow as a rate, maybe. Yeah, exactly. So our flow would increase because we have a greater difference in pressure, right? So before we had our difference in pressure. Calling me from Memphis, Tennessee. Nobody I know. Okay. So before, actually, and that shouldn't be an equal sign. So I'm going to use this because they're going to have an approximation maybe. So before we had our difference in pressure as 50 over whatever our resistance might be. And now we have our difference as 100, right? So if we did that calculation, if we didn't change the resistance, we'd get a greater flow. So what about this second version? what's going to happen if both A and B are increasing? Are we going to see a change in the flow? No, right? So we're not concerned with our absolute pressures here. We're concerned with that difference. I want to make sure you remember this word directly proportional because it will come up in questions sometimes. So we're saying here that our flow is directly proportional to our pressure, right? So it's directly proportional. What that means is that if our pressure goes up, our difference in pressure goes up, our flow goes up, right? So they're going the same direction. You increase one, the other increases. That's basically what we're saying when we say that. Okay. So before we get started talking about the resistance, we're going to be paying attention to the pressures in specific locations in our vasculature. So let's remember how our blood flows through circuits. We're not going to worry about valves or anything right now, but we do want to remember just kind of the order of flow. Okay. So when we start out with our blood flow, start out, what's this location called here? Yeah, our right atrium. Okay. And this will be helpful to remember for anatomy because you will be looking at hearts this semester. After the right atrium, where are we going? The right ventricle, right? We're going to a ventricle, but we're staying on that right side. Right ventricle next. Then what? Where are we going next? We're going to an organ next, basically. Yeah, exactly. So we're going to do our lungs. And what do we call this loop that I'm drawing us here, basically? Yeah, if the pulmonary artery is coming out, we have our pulmonary veins coming back in. And overall, we call this our pulmonary circuit, right? That's our pulmonary circuit. So where is the blood in those pulmonary veins coming back to the heart? Yep. Left atrium. Okay. So next, we got one more piece of the heart left. Yeah, exactly, our left ventricle. Okay. This is where we leave for our systemic circuit, right? So next, we would expect to see our aorta. I'm going to draw a curvy because that's what it actually looks like. Right, so it has this arch. And then we're going to see it go out to all our other organs before it loops back up to the right atrium. We have these two circuits involved with opposite sides of the heart, but our flow through all of these is going to be continuous, right? In that order that we drew them just now. So we could draw arrows along them. All right, our blood is going like this, right? Swirling around and doing this kind of loop thing. Okay. Now this is important to remember because we are going to be thinking about some differences between the pulmonary circuit and the systemic circuit, but it's going to be important to realize the blood has to be going all the way around kind of at a constant rate, right? We're going to have the same flow going through our pulmonary circuit as the systemic circuit because this blood is continuously moving in this cycle. We can't have it like building up in the lungs because it's going slower or something, right? That wouldn't let us have this closed loop working. The other thing we're going to be talking about in a little bit, but is related to the flow of blood, we're going to see when we talk about the vasculature, those blood vessels that we've just drawn as loops here. We're going to be thinking about arteries. We're going to be thinking about arterioles. We're going to be thinking about capillaries, venules, and veins. I'll be talking about some of their physical properties as well. So did that reminder first because when we're thinking about the pressure gradient across the cardiovascular system, usually we're talking about the systemic circuit, but we'll be thinking about both systemic and pulmonary circuits. We're going to be measuring that pressure to calculate our difference in specific places. So for our cardiovascular system, when we're thinking about that pressure difference, we're comparing the pressure in the aorta, right? This is a large artery, largest artery. This is where we measure our mean arterial pressure, MAP, which we spoke about briefly last semester. And then our opposite end of the loop, where we come back to the heart, come back to the right atrium, we're measuring pressure in the vena cava, which you'll see in lab. So here we can use a, I think, new term. Have we talked about central venous pressure before? I don't think we've talked about that yet. It's pretty much the same thing as the mean arterial pressure in terms of measurement. It's just at the opposite end of the loop. So we're measuring it at the vein coming into the heart. So central venous pressure is CVP. Our difference there, so our difference between the pressure in the aorta and the pressure in the vena cava, or between MAP and CVP, is going to be our difference in pressure for the flow through our cardiovascular system. So given what we know about flow through the cardiovascular system, and maybe something we know about arteries and veins, which of these two things do you expect is going to be higher, MAP or CVP? Yeah, exactly. So our mean arterial pressure, arteries carry a lot of pressure. The aorta carries a lot of pressure, which we looked at how that creates effects in valves last time, and we'll be thinking more about how that fuels blood flow through the cardiovascular system. So your mean arterial pressure will be something like 85-ish. Do that 8 weird. And CVP is somewhere around 2. As we come into the right atrium, it's almost 0. So usually we kind of wave our hands and just pretend that CVP actually is 0, because that makes our lives a little easier. We can just think about the pressure in the aorta when we're doing calculations. So that'll help us later, but don't forget that this is a pressure difference. Even when we start just focusing in on MAP, it is important that the other end of this system exists. We don't always focus on it, but sometimes it becomes important in different pathological conditions. So questions thus far about this pressure stuff? All right. So here we're taking a look at the pressure across the systemic circuit and the pulmonary circuit. So what we have listed out along our x-axis, right? We have our different types of blood vessels, so the different parts of the vasculature. So we're starting with our arteries. Maybe I'll number them for us. All right, so number 1, we have our arteries, and then blood would flow into the arterioles, which are smaller. And we're going to go to the capillaries, which is going to be our site of exchange for particularly oxygen and carbon dioxide we'll be interested in. We've seen capillary beds before. Does anybody remember what unit we saw capillaries in? Yeah, we saw them when we were looking at the endocrine system, right? When we were thinking about the pituitary gland, we saw those 2 capillaries, or 2 capillary beds linked together there. So we have seen capillaries before, although we didn't talk too much about exactly how they work. So on the other end of a capillary, we have a venule. So the word even looks like it's just a little vein because it is. So then we have our veins, which refer to the heart. What are some things you might notice about this graph? Anything at all? Differences between the systemic circuit and the pulmonary circuit, differences between different parts of the vasculature. How might you describe either of these lines or comparing them?
farther you get away from the heart, the lower the pressure.
Yep. As we get farther away from the heart, we have less pressure, which is great, right? Because that means our blood is going to want to return to the heart. How about a comparison between the systemic circuit and the pulmonary circuit? Yeah.
And drop faster.
Yeah. So our systemic circuit has high pressure and drops fast, which means we're going to have a big difference in pressure across that circuit, right? A big difference in pressure. So this is part of why I wanted to point out to you that blood does have to flow through both of these circuits in order, right? We have to go to the lungs first to pick up our oxygen, and then to the rest of our organ systems to drop off that oxygen, basically. But in terms of what we know about flow right now, this would create a problem, right? So our flow, right? I said it was directly proportional to a pressure difference, right? So right now, what would happen? How to phrase this question? Would we expect with just this information for our flow to be the same between the systemic circuit and the pulmonary circuit? No, right? Because we have a big difference in pressure across that systemic circuit. And then we have a littler difference, smaller difference, a lesser difference across the pulmonary circuit. So what do you think is going to explain that? How are we going to make it so that we can have that blood all flowing through the pulmonary circuit and then the systemic circuit without backlog? What other property do you think we're going to have to pay attention to here? As a hint, I've only drawn part of that equation, right? Flow isn't actually equal to the difference in pressure, is it? What's the other part of that equation? Yeah, exactly. All right, so we're going to have to account for the resistance as well. So which of these systems would you predict is going to have higher resistance, knowing that the equation looks like this? You could take a second. Actually, a hint, because I've noticed it's something I always do, and maybe not everybody does this, but I like learning the equations because I always put in dummy numbers, right? Instead of actually thinking about this just in my head, I like to put in lots of 1s and 5s and 10s and just see how the math works out to make life a little easier. I have confidence someone can tell me which of these is going to have higher resistance than the other. Go ahead.
Well, I returned that systemic. So now I switch my answer just because you got me thinking about like the direction for the.
Okay, maybe I confused you there. Yeah. So let's say our difference in pressure here. Having said this, right? Okay, so let's say the difference in pressure across this system, across any system. Okay, let's do this. Let's say a difference in pressure is 10. If we have a resistance of 2, what's our flow going to be? Yeah, 5. Okay. So now let's say we have, I'm doing this on the fly, sorry about that. Let's say we have a resistance now. Let's pick that same pressure actually. 10, let's say our resistance is now 5, so we have a higher resistance. What happened to this number? Yeah, it goes down. So now we have a flow of 2. I'm sorry, you may have to think about this a little bit after class and we'll come review this. I feel like I may be confusing you now. But what I'm saying basically is that as the resistance goes up, the flow goes down. So because we have a really small difference in pressure across the pulmonary circuit, to end up with the same flow, we're going to want to divide that by a small number. But we'll come back to that. Okay. So the pressure gradient in that systemic circuit is really big. The aorta has a lot of pressure, right? The pulmonary circuit, we have a lower pressure gradient, as we just saw on that graph, right? So our right ventricle isn't pumping that much pressure into those pulmonary arteries. However, all our blood is flowing to the lungs, and then all of it is flowing to the systemic circuit. So the way that this is possible is because that divisor, that R value, that resistance is less than the systemic circuit. I'll come up with some better dummy numbers in the future to kind of show us why this has to be true. But this gets us to our second kind of thing we want to realize about the flow. While we were directly proportional, our flow is directly proportional to our pressure difference. Our flow is inversely proportional to our resistance. So as you just said, that means that if the resistance goes up, what happens to the flow rate? Yeah, exactly. So anything that increases resistance is going to decrease flow, whereas anything that increases our pressure difference increases flow, right? So our arrows go the same way on flow and pressure differences, opposite directions for flow and resistance. That's going to be important as we go through, not specifically for like math reasons, but as we talk about, different hormones that can affect vasculature, different ways that vascular is going to change its resistance. We're going to want to know what does this do to the blood flow through these different parts of the cardiovascular system. Okay. There are multiple factors that go into creating the resistance in a blood vessel. It's not just one specific thing. Resistance isn't just an individual physical property, it's kind of a combination of things. Fortunately, not all of these are super important when it comes to vasculature, although they all do feed into the actual calculation of our resistance. We want to take a look at what these properties all are first, so that as we go through in the future, we can think about which of these can vary in specific situations. So the first thing, and the most important thing we're going to see varying our resistance level, is the radius of the vessel. So when we say the radius is changing, right, we can either have a narrow little blood vessel, or you can have a big, wide blood vessel. So big radius, or a little bitty radius. So we have this equation at the bottom here. Which of these two do you think would create a higher resistance given this equation? Assuming all these other variables stay the same. Is this going to be directly proportional or inversely proportional here? That radius. So the radius here in this equation is specifically that R. Yep, it's inversely proportional. So does that mean a high radius creates a high resistance or a low radius creates a high resistance? Are they the same or opposite? I heard you whisper it. Yeah, exactly, opposite. So they're opposite, they're inversely proportional. So that means that our narrow little blood vessels are going to have higher resistance. So if we want to increase the resistance of a blood vessel, increase the resistance of our system, we're largely going to do this by changing the radius of our blood vessels. We're going to decrease that radius to increase resistance.
Are we gonna have to memorize these equations for these gaps?
You definitely not this one. I'm thinking about the other one. What you're going to want to be able to do is to relate changes. So like, I will ask you, does this situation that increases radius increase or decrease resistance, right? So you don't necessarily have to memorize this equation to tell me the answer to that, but knowing parts of these equations will help you for that reason, because it's just kind of one less step. But if you find it easier to just try and memorize a whole big list of situations that could either increase or decrease, that is another way to get to it. Personally, I just like to remember as few things as possible, which is why I like equations. Okay. So other things that can factor into the resistance here. Next, we have our length of vessel, our length. We made something longer. We increase or decrease the resistance.
Wait,
Increase, right? So length and resistance would be directly proportional. Now, do you think we're often going to see how long our blood vessels are change? No, right? So we're mostly going to ignore length. So we won't talk about that too much. Our third one is the viscosity of the fluid. So here's our viscosity of the fluid. So viscosity of a fluid is kind of like how thick and sticky it is, right? So if we increase the viscosity, the resistance is going to go up or down, increase or decrease. Same as length, right? So if the viscosity increases, the resistance would increase as well. We're not often going to see this one either. Sometimes blood viscosity does change based on the amount of red blood vessels, the amount of proteins in the blood, but this usually should be constant, especially for an individual person. So for each of these, we can also kind of think of some everyday relationships that might make it a little easier to remember. So when we're thinking about resistance, last time I said it was kind of like friction, right? Partially because it's that inverse relationship with flow, right? Like more resistance makes it harder for things to flow, right? So when we think about that radius of the vessel, think about like a little coffee straw or like a big straw for like bubble tea, right? So which of those gets more liquid into your mouth faster? Right, the big bubble straw, right? Like a lot, that's because it has a larger radius, right? Like it's wider. Sometimes I think about like doorways or hallways like this too, right? You know, the tunnel up over towards tower, there's that ramp as you start to go towards Stormstone, right? Often when I'm going down that ramp, I think, gee, I really wish this were wider, then we could get through it much, much faster, right? So that's the same kind of thing that's happening in your blood vessels. If you increase the radius, if you increase that space, things can move faster through it. The third one, the viscosity, is the other one that we can kind of think about real life examples for. I'm not going to think much about length because it's not really relevant to our study of physiology. If we think about viscosity of fluid, we can think about, say, drinking like a soda versus drinking a milkshake, right? Harder, slower to drink a milkshake, especially if you're slurping it through a straw. These rules govern resistance throughout the world, not just in our bodies, which is why we can kind of make these comparisons. This is just the equation again, so I'm not gonna worry about it right now. Okay. So now we have one of these examples that your textbook likes, with these columns of water, little tubes connecting them. So technically, these columns of water, by the way, in case you see the term, are called hydrostatic columns. We'll talk about them a little bit in the future when we start to talk about hydrostatic pressure, but we don't have to worry about it right now. So what we're looking at here, we can see these two columns, different heights, which means we would experience different pressure, right? So we're given that the pressure difference is 40, okay? But what we can see here about the flow, that the flow through A, 20 milliliters per minute, the flow through B is only 10 milliliters per minute. Take a second and answer this in your head, and then I'll ask someone to answer for all of us. But what do you think the difference between A and B is that's creating this difference in flow? Okay, let's have someone from the back this time. Who wants to answer? All right. Anybody? I don't like to call people. Okay, so let's just describe the difference here then. All right. So what do you notice about A versus B? I'm gonna highlight something. All right. What's going on here? Yeah, exactly. We have a wider tube here, right? So we have a greater radius, right? Greater radius. Okay, so remember now, going back to the previous one, or sorry, the previous equation, right? That our resistance, which is our big R, right, was inversely proportional. I don't like remembering that whole big equation either, to our radius, right? So as we increase that radius for A, we have a bigger radius, meaning we're dividing by a bigger number, meaning we have a lower resistance. That's why we have a greater flow, because our flow equation, we have that same difference in pressure there for both of these situations. It stays 40 for both of them. But we have differences in the resistance because we have differences in the radius. So for A here, we have bigger radius, which means we have lower resistance. And here for B, we have smaller radius, higher resistance. So when we divide by that bigger number for B, we get a smaller flow. So low resistance for situation A, high resistance for situation B. This means that even with the same difference in pressure, we're changing our flow rate. And this will be important when we think about our organ systems, because we're going to see that we're going to want to vary how much blood gets to different organs in different situations, right? Like we talked about last semester, how sometimes you're going to want your skeletal muscles to be getting more blood flow, right? Like when you're in these fight or flight situations, you're trying to run away from something. You're going to want to be able to do that by changing our resistance and then therefore changing the flow to specific parts of our body. And we'll talk about that in detail when we get there, but like that's why we care about this stuff. So the specific part of the vasculature where we're going to be regulating the blood flow is at the arterioles. So the arterioles are those sort of smaller branches off the arteries, right? They're actually microscopic, but this is where we're going to really be able to substantially change the radius of the vasculature. So we're going to regulate the radius of the arterioles and maybe some small arteries in order to change resistance in our system. So we have specific words that we use for this. So if we decrease the radius, right, so we have a smaller little arteriole, a smaller tube, we call that vasoconstriction. Vaso for vasculature, constriction for that fact that we're squeezing it tighter, squeezing it smaller. So vasoconstriction decreases the radius of a blood vessel, which in turn increases the resistance because of that inverse relationship, right? So our resistance was inversely proportional to our radius. All right, so when we had, so when we decreased our radius, we increased the resistance. The opposite is vasodilation. So again, vaso for blood vessels, dilation just means to expand, to dilate. Like when they dilate your eyes, they put those drops in your eyes and your pupils get really big. So vasodilation means that we're increasing the radius of something, so we're making it bigger. So as we increase the radius, right, so we increase the radius, which means we're going to decrease the resistance because we have this inverse relationship. So in the pulmonary circuit, as we said before, one of the features of the pulmonary circuit is that the whole system, to begin with, has a different amount of resistance than the systemic circuit. So in our pulmonary circuit, we have a little resistance, okay? And this is partially due to the vasculature as well. But mainly we're going to be ignoring the pulmonary circuit until our pulmonary unit next time. But we do just want to keep in mind that we have a different pressure gradient, and therefore we have to have a different kind of amount of resistance in that system. Okay. So we're going to be focusing on the systemic circuit pretty much from here on out until we get back to the lung. So what we're going to be talking about as our measure of resistance throughout the system is something we term total peripheral resistance, which we're going to abbreviate TPR. So total means we're adding it together, right? So we're not going to spend a lot of time thinking about, okay, so what does this one single little arteriole in your wrist do? When we're thinking about effects on big picture variables like blood pressure, right? We care about how much resistance there is in the system as a whole, right? So those are the things we're going to be wanting to measure for people's health. So we want to know about the whole system. So the total peripheral resistance is the resistance across a whole network of blood vessels. And it depends on the resistance of each of those individual vessels kind of added up. The flow through the network, just like the flow through a single tube, is going to vary with the resistance of that network. So often we'll talk about vasoconstriction not as affecting one single arteriole, but as affecting a network generally. But it works the same way as those individual relationships did. So we have vasoconstriction. We're having those smaller radii, increasing resistance, decreasing flow. Our vasodilation has the opposite effect. So vasodilation, bigger radii, lower resistance, increased flow. Right? That's because we've stepped out from that relationship between resistance and radius back out to that flow relationship to resistance. Right? So we toggle a lot what's in our numerator and what's in our divisor for these equations. So now we're going to want to map that onto things we might actually measure in a person. Right? So our overall flow through our systemic circulation is actually just our cardiac output. Right? Our cardiac output was what? What's our definition for cardiac output? Anybody remember?
So through volume.
Oh yeah, we don't need to remember the equation for now. But yeah, perfect. For our purposes right now, it's just all that blood coming out of the heart in a minute, right? It's our rate. So our flow here is cardiac output. Our difference in pressure, we're approximating as the mean arterial pressure because we're assuming here CVP is around 0, right? So difference can just be measured by the mean arterial pressure because that other end of the system has a negligible pressure. And then R is our total peripheral resistance. So the additive resistance of all the blood vessels in the body. Really, that's going to be talking about the arterioles because that's what we're able to vary in terms of their radii. So if we reshape this equation, right? So flow equals difference in pressure equals difference in resistance, right? Our flow is the cardiac output. And we're one by one kind of subbing these variables in, right? So we replaced our delta P with MAP, that mean arterial pressure. We could put on the CVP there, but I'm going to write it. And then I'm going to cross it out because it's 0. But just don't forget that you have veins. Okay. So MAP divided by resistance. Specifically, we're talking resistance and those arterioles throughout our system, which we measure as TPR. So that's how we got to that second equation at the bottom. So next, we're going to start thinking about the ways that our blood vessels vary and how that affects what happens in those specific blood vessels. So this is in the next packet. I'm just going to briefly show us the first slide. Actually, we just talked about it already. So let's, as a team, just remember listing the order of blood vessels, and we'll stop there. So what is our largest blood vessel coming directly away from the heart? What type of blood vessel would that be? Our arteries, yep. So from the arteries, what are we going to branch out into? Yep, arterioles. So when we say that, see that ending eoles, that should indicate to us that we're thinking about something smaller. Both of these are flowing away from the heart. What are we getting into next? Capillary bed. Okay. And now we're going to start our return to the heart. So what comes next? Yep. Venules. And then vein. Yep. And then we're going to return to our right atria. So next time we'll talk about different physical properties of these blood vessels and how we can vary them and how that's going to let us adjust some of these larger measurable characteristics.
The show equals the equation.
Yeah. This one?
Yes, please.